Struggling to find a white chalk. Oh, you found it. Thanks. Okay, well, thank you. Um, so I'll maybe give an outline of the talk, so that you. Well, anyway, so first of all, I'm going to outline the result and like motivate. Which is kind of in the spirit of algebraic geometry. And then I'll tell you how that is actually symplectic by also going through some basic things in symplectic topology. So kind of intro in SG. And then I'll try to outline the proof. Okay. So section 2 would be probably very boring for the symplectic geometers, but it's important for people who don't have the background. So first of all, introduction. So in symplectic geometry, we study manifolds, but in algebraic geometry, people study varieties which can have singularities. And one basic class of singularity is called isolated hypersurface singularities. So these are an isolated hypersurface singularity is basically a singularity that could be an isolated singularity that is expressed as, in the following, as a hypersurface, that as singularity that appears as a hypersurface, a singularity. Okay. And these things are very well studied historically, and even classified. To a certain degree. So Arnold introduced a notion of complexity called modality, which is, so roughly speaking, a number that tells you how mild or nasty the singularity is, roughly speaking. And it's a positive integer, well, 0 as well. And he classified these isolated hypersurface singularities up to modality 2, I think. And the modality 0 ones, it's the most simple singularities, and they're very famous, ADE. And for example, the A singularities have the polynomial expression of the following form. The M singularity looks like this. Okay. And their corresponding polynomials for D and E singularities as well, but I'm not gonna write it down. Anyway, so AD singularities, maybe you've heard somewhere. And modality 1 singularities, they're also classified, and there are 3 types. So one is called, oh, this is I think they're called elliptic simple singularities. And the second family is called, I forgot how they're called, but TPQR. And 14 exceptional singularities are that has an interesting duality property. So, and the list continues, from modality 2. There are many others, but basically these things have been studied historically. And all right, so that was isolated hypersurface singularities. And a basic question in algebraic geometry is like a rough basic question. Given a smooth variety X, what type of singularities can X develop? I'll precise the question in a minute, but basically you start from something smooth and you kind of start deforming it, and
Sorry, could you switch the board?
Oh, sorry, I'm very sorry.
Yeah, no worries. Thank you.
We're here. So yeah, you start from a smooth variety and you start deforming it, and at the end you want to understand what kind of singularities it might get, and to mathematically formulate this procedure, so these things are in mathematics, it's called degeneration. Degeneration. So just recall what it means, but they are maybe on this. So we say that a smooth variety X degenerates to a singular variety X0 if you are in the following situation. So we want a family of we want a map from a big space curly X from to the plane flat prism, such that above 0 you have this limit singular variety X0, and above some point that is not 0, the fiber of this map I is a variety that is isomorphic to the smooth one you plotted. So write that down. My one of 0 is x0. My one t x for some a. And I think I also want that this 0 and a fiber over 0 is the only singular fiber. So if t is non-zero, then you'll get something smooth. And I think usually people also say that all total space curly X doesn't have singular locus other than the singular locus. I don't think I have to be that precise today, so get about that. So anyway, the problem that I stated over there, it's it means if X degenerates to X0, what kind of singularities does X0 have? And I will go back and tell you more about it, but just for example, Duval studied the case of surfaces, false Benzel surfaces, so Fano. Final surfaces. So we'll get back to this after. Okay. Okay. So I spoke about singularities and degenerations. And I also want to review a little bit about quantum cohomologies. So Professor McLean spoke about this yesterday, but once again, we just quickly set notations and everything. So this invariant, well, this algebra is something that is studied in common between algebraic geometers and symplectic geometers. And it's defined for, well, projective, let's say projective variety. And it's given a projective variety, you get an algebra, which is as a vector space. It's just the singular homology, singular cohomology, but with some special field, coefficient field called the Notkov field. And it is not very important. I mean, it doesn't matter if you forget what this Notkov field is, but I'll just write it down. So it looks something like this. So I use a convention that is slightly different from what it was used yesterday. So at the beginning, you have a complex number, and then you also put a formal variable t with some real number on top that keeps going, getting bigger and eventually goes to infinity. And the reason, I mean, as a vector space, it's just this homology, but it has a special product called the quantum product structure. So this star, the quantum product instead of the intersection product. And as it was explained yesterday, if you look at the product of classes A and B, it's like it's something more complicated than the intersection product. You start from an intersection product, but you also consider intersections modulo holomorphic spheres, rational curves. So this is let's say this is a homology class representing this picture is a homology class representing the Poincare dual of A, Poincare dual of B here, and then you keep track of all the sphere like intersection with some sphere being lying in between intersecting these guys. So it's more complicated than the usual intersection product. And this formal variable is here sort of to keep track of this sphere, the area of the sphere.
What is it? A and B, it's A cup B.
Yes, here.
Yes, it's
Yeah, you're right.
And you're doing small quantum cohomology, like
Exactly,
I
yeah.
did yesterday.
Yeah. And so because the product structure is more involved and rich, it gives you so because of quantum product, the algebraic structure of the quantum cohomology is more interesting or more complicated or interesting or involved than the usual singular homology. So for example, there's a famous structure called the semi-simplicity that's been studied a lot by algebraic geometers. Studied a lot by people like Manin, Bayer, Dubrovin. And Dubrovin has a famous conjecture concerning semi-simplicity, for example. And so what is that? So we say the quantum cohomology is semi-simple if it splits into sum of fields. So the split is with respect to the quantum product. So meaning that if you take classes, a class 1 in Q1 and a class in Q2, then their product are going to be 0. It's split with respecting the product structure, not just as a vector space way. Okay, so I'll state what I want to.
Actually, I think you want to assume this. You want to restrict to the even part because that's the commutative one.
Okay, yeah. Let's be rough. And yeah, okay, I'll state the thing I want to discuss, but later on. So what did I want to say? Okay, so suppose we have Fano variety, a smooth Fano variety. And let's assume that the quantum cohomology of X is semi-simple. So I assume a condition on quantum cohomology, and let's consider the situation where X, smooth variety X that we're given, degenerates to a singular Fano variety. With the basic class of singularities that I introduced at the beginning, namely the isolated hypersurface singularities.
Sorry, could you move the camera to board one?
Sorry, I forget. So, as I said at the beginning, these isolated hypersurface singularities consist of ADE and all TPQR and other things. But the claim is that under this assumption of semi-simplicity, the singularities that appear in the limit have to be the M singularities. So under this semi-simplicity assumption, you're not going to have D singularities, E singularities at the end, or like any TPQR. It has to be an A-type singularity. So I'll get back to the result of Duval that I wrote here. So let's say history. So Duval studied the surface, the two-dimensional case of this situation. So he studied he wondered if you start from a Fano surface, so the Petzl surface, and degenerate it into a singular Fano surface, a singular Petzl surface, what kind of isolated hypersurface singularities you can get. And let me remind you that Professor Lee spoke about, as explained to us, Fano surfaces, there are other stuff, but mainly they're blow-ups of CP2 and with at K points, and blow up in the sense of do some McDuff explained at the beginning. Points. So yeah, Bob proved that if the number of points being blown up is between 0 and 4, then you only get AM singularities. While from if you blow up points more than 4 points, then you do get D or E as well. Like you get A, but also D. And also this is the so for the spectral surfaces of the first category, the quantum cohomology is actually semi-simple. And for the second category, if you start blowing up a lot of points, then they're not semi-simple. So you see that here, the semi-simplicity forces AM singularities and not that they exclude DE singularities. And you see that, this DE only starts to appear as soon as you break the semi-simplicity. All right. And so that was section 1. And so far, apparently there's no symplectic geometry, but actually the proof or the argument is symplectic geometry. So I'll explain how this is related to symplectic geometry.
If it's variety is not follow, quantum cohomology cannot be semi-simple, or
Yeah, I think it's only for Fano. Right. Yeah. So a quick intro to SG and also like notation setting, and also providing important things about the argument.
Semi-simple as you put it.
the text structure could be different. Also, even on this manifold, it's monotone. This is also this one where Seidel, I think, use the semi-simplicity to show that Lagrangian twist. One case less bigger than 5, at least 5. It's not the square is not identical. Maybe those
Oh, okay.
I mean, here the non-semi-simplicity show the Lagrangian twist square is not identical for hypersurfaces. It's CP3 is dividing. Case 5 is the first case where you see this phenomenon. Well, CP2.
Thank you. Thanks for providing some extra information. So I'll try to explain how this is related to symplectic geometry for the algebraic geometers, especially. So first of all, why in this? So first of all, important thing is that projective varieties are symplectic manifolds. And why is it? That's because given a projective variety, you can just, so you choose an embedding to a projective space, and then you can pull back Fubini studi form, which is the symplectic form for the projective space, and then you get a symplectic structure on the variety X. So projective varieties are symplectic manifolds. And there's a very special submanifold symplectic geometers like to study. Special submanifolds. called the Lagrangian submanifolds. Which I don't think there's a counterpart in algebraic geometry, because it's something that requires a symplectic form. So this is something very symplectic. And what are they? So we L submanifold L is a Lagrangian. If the restriction of the symplectic form on it vanishes. Okay. So to give you an example, let's take P1 or the sphere and consider the equator. Then, well, there's only one direction for the equator. And obviously, because symplectic form is non-degenerate, this restriction will vanish. So this is a Lagrangian. Okay, the equator is a Lagrangian. And more generally, you can think of objects like RPN inside CPN. So the fixed locus of the involution defined by the conjugation, for example, or Clifford torus, which is defined as set like this. And you can see that the restriction of the symplectic form, the Fubini-Studi form, vanishes because Fubini-Studi form can be written like, I forgot the constant factors, but something like this. So you can see that if you restrict it, it's going to vanish. It's a Lagrangian submanifold. And these middle dimensional submanifolds are sometimes very useful to say something about the total space. Like even though it's just a submanifold, it can tell you a lot about the whole space geometry. Okay. And so for okay, and then okay, so now I'm going to review once again Floer homology, Floer theory, which was already done by Professor McLean, but I'm going to maybe do it again because my purpose and also yeah, I will need it. I will maybe state it a bit differently. So first of all, what is Floer theory? So basically, so I'm going to construct a homology like algebra from time-dependent function on the manifold. So this is called the Hamiltonian time-dependent function on manifold, a symplectic manifold. And then I'm going to build an algebra that is called Floer homology. X denotes it like this. And the relevance of this thing in my talk is that before even telling you what this is, this Floer homology is ring isomorphic to the quantum cohomology. So, you know, this Floer homology is really closely related to the quantum cohomology. I think this is called the PSS isomorphism. And let me remember what quantum Floer homology is, also by maybe even explaining the original motivation or constructing such a thing. So it started from a question in dynamics, let's say. So given a Hamiltonian, H, we can define a thing called the Hamiltonian flow. So that is done in the following way. So you think of the derivative of the function and get one form, and then by using the non-degeneracy of the form, you get vector field. This is called the Hamiltonian vector field. And then you get a flow from the Hamiltonian vector field. Vector field called Hamiltonian flow. And then you want to study the dynamics of this flow. That was the original question in symplectic geometry. And there was a conjecture by Arnold saying that this Hamiltonian, I forget, I forgot to say something. But the time one flow is called the Hamiltonian diffeomorphism. And Arnold conjectured that this Hamiltonian diffeomorphism should have a lot of fixed points. So he said it should have at least number of the Benty numbers, for example, the fixed points. So this Hamiltonian diffeomorphism has a very strong rigidity property. And for example, it is often the case that the Lagrangians of Lagrangians of manifolds, which are just middle dimensional, some middle dimensional submanifolds, they're often non-displaceable by Hamiltonian diffeomorphisms. So they're very special and rigid and very special. And Floer homology was introduced to solve this conjecture. And maybe that's because, and maybe you when you saw this inequality, you maybe thought about the Morse inequality, where, like in the book of Milner, where he bounds the number of critical points of a Morse function by the sum of Betti numbers, for example. And Floer homology is basically the Morse theory for symplectic geometry. And I'll maybe draw a table to compare Morse theory and Floer theory. So in Morse theory, you start from a Morse function on a smooth manifold M. And look at the critical points and build a complex. So the complex is spanned by the critical points. And then the differential of this complex is defined by counting number of gradient or anti-gradient trajectories from one critical point to the other. And then you count them, and then you get a Morse homology that turns out to be isomorphic to the singular homology. And therefore, the number of critical points of F should be at least the number of Betti numbers, because each generator would correspond to a critical point. And then you have at least the Betti numbers of generators. So that was Morse inequality. And in Floer homology, instead of the Morse function, you use this special function called the action functional, which is defined on a very big space. So it was introduced yesterday, but it's this. So it's the set of contractible loops on M, symplectic manifold X, that is so contractible. And I take cover, so it's a loop, contractible loop, but with also capping. So a disk that has a boundary loop. And then I'm not gonna actually, you don't need to know what this action functional is, but the critical point of the action functional corresponds to the fixed points, in the sense that the critical points are actually the orbit of the Hamiltonian flow that would come back to itself. Okay. So by using this analogy, the Floer complex or the Hamiltonian H is going to be like this. Well, it's spanned by the critical points. And now we have, let's say we have two critical points like this, and we count the anti-gradient flow for this functional, which actually looks like a cylinder, as it was explained yesterday. And you count them, and you get a chain complex, which is highly non-trivial. And then you end up getting some homology. And as I said, isomorphic to, well, quantum cohomology. But as a vector space, the usual singular homology. So Floer answered this Arnold conjecture by saying that, okay, the critical points of the action functional, those are the fixed points of the Hamiltonian diffeomorphisms. And he had this algebra coming from the generated by the fixed points that is isomorphic to the quantum cohomology. So there's at least this many non-trivial fixed points, and then he answered the conjecture. Okay. And recently, there's a quantitative version or there's been a lot of refinements and additional information on studying these days. And I'm going to introduce one of those, namely spectral invariants. So, let's say okay, so here actually in Morse theory, Morse homology, let's go back to that case. We can given a real number R, we can consider the restricted complex that only uses that only catches critical points that have value less than tau, the given real number. And this will not change the theory because the boundary, the differential or the boundary map is defined by the anti-gradient flow. So the differential actually preserves, it stays in this complex. It's only gonna use critical points whose height is lower than the one here. So we can actually define this filtered Morse homology with this filtration tau for any real number. Okay, and same for Floer homology. We for every real number tau, I can restrict the critical the complex to orbits that have action less than tau, and differential only decreases the action. So that is not going to be a problem, and I get a filtered version of Floer homology. Okay. So you can define filtered or homology. And there's a number, a set of numbers called the spectral invariants that is so in the Morse case, let's say you have f is the Morse function, and given homology class A, you can ask when the given homology class start to appear in the filtered. So it's the height where you start seeing the A. Bit more precisely, well, as I said, there's this filtered Morse homology. That gets mapped to the cohomology by reduced map coming from the injection. And here you have an isomorphism between Morse homology and singular homology. And I'm given a class here, and I map it here. And then I'm asking when, at which level do you start seeing this class, okay? And that real number is the spectral invariant for Morse homology. So for example, the fundamental class, the spectral invariant corresponding to the fundamental class, this will be the maximum, the Morse function. And we do an analogous thing in Floer homology, Floer version. So in this case, we don't have a Morse function, but a Hamiltonian.
Sorry, so this depends on a choice of an isomorphism between Floer and ordinary cohomology, or is that canonical in some way?
Yeah, it's canonical, yeah.
Okay.
So instead of a homology class, I assign a quantum cohomology class. And it's the same thing, it's the infimum. Well, I'm going to be very rough here, but we have the filtration tau, and I can, kind of map it to the full Floer homology group, which is ring isomorphic to the quantum cohomology. And I'm given a class here, and I look at its counterpart in the Floer setting, and then I start increasing the filtration level and wait until I start seeing this guy. And that's called spectral invariance. And okay. Oh. And as I said, Lagrangians of manifolds manifest surprising rigidity phenomenon properties. And there are many ways to capture rigidity or to express rigidity, but I'll introduce a quantitative way to express a symplectic rigidity of Lagrangians of manifolds in the language of spectral invariance. A quantitative expression of symplectic rigidity for Lagrangians. So I'm going to, and this theory is due to Entov-Bolterovich. So what did they do? First of all, I want to define a special function by using invariance. Define the following, but I have to assume something. Suppose you are in the following situation. So suppose your convective variety or symplectic manifold has a very nice property that its quantum cohomology splits into a field. It has a field component, let's say. And this A part, it could be whatever algebra. Oh, right. I'm sorry. So suppose you have this some specific condition on quantum cohomology, and then you split the unit. So this is a ring, it has a unit. It's the fundamental class. I'm going to write it by 1x. Let's say you split the fundamental class with respect to this split the ring structure. And I look at the idempotent that is the part of the field, okay? And Entov-Bolterovich defines the following function. So it's called, I'll call it zeta E, where E is this idempotent of the field component. And it's a function from the set of smooth functions on X to the real Y. And so I start from a function H, and the real number is defined in the following way. So first of all, as I said, there's C is the spectral invariant, and I look at the spectral invariant for this idempotent E and A times H. And I look at, so I basically look at the asymptotics. I look at the spectral invariant of K times H with this fundamental, with this class E, and divide it by K, and look at its limit, okay? Then it turns out that this limit exists, and that will give you a real number, and that is how the function zeta is defined. So this function, it comes from Floer theory, and it's a real number, okay? And here's a definition of the rigidity, like rigidity, quantitative rigidity. So let L no. Okay, so let K be a subset, any subset. And we say that K is heavy with respect to the class E if we have the following. So this function zeta, it has nothing to do with this just comes from Floer theory of the entire manifold. It has nothing to do with the subset K. But if we just happen to be able to bound this quantity by looking at the value of X on K, then we call it heavy. So let me remind you that really insists that this zeta function zeta has nothing to do with K. Miraculously, say something about the value of this function just by looking at value of the Hamiltonian on that set with cohomology. And we furthermore, we say this set is super heavy with respect to class E if we can bound from above the function zeta. Okay. So this rigidity, this quantitative expression of rigidity will be useful in the following.
When you say super heavy, you mean if in addition to being heavy, this satisfies this quantity. So the lower and upper bound.
Yeah, this is stronger. You can actually prove that if you have super heaviness, this implies but yeah, it is super heavy is a special type of heaviness. It's strong. And one super basic exercise, but useful, is that two subsets, disjoint subsets, A and B, well, K1 and K2, cannot be both. Cannot be both super heavy with respect to the same class E. And it is very easy to see this. So suppose you have two disjoint subsets K1 and K2, and let's suppose they're both E super heavy, and I'm going to get a contradiction. So you take a function, so this holds for any, this has to hold for any Hamiltonian. So I'm going to take a Hamiltonian that is 100 here, that takes value 100, and that takes value 0 on K2. And then I'm going to study the value of zeta E with respect to H. And then by using the super heaviness of K2, this value has to be bounded from above by the value H takes on this set, which is 0. So it's 0 by looking at K2. But then, as what's being said, it's also heavy, so it has to be bounded from below by the value it takes on K1. So this is 100. So this is a contradiction. So two disjoint subsets cannot be super heavy with respect to the same class. Okay. All right. So then these are the tools that I need for my argument, and I'll sketch the proof. And I think I wrote in the title thing that I will explain the quantitative rigidity for Lagrangians of manifolds, but this thing applies to any subset. But it happens often with Lagrangians. That's what I wanted to say. So let me remind you maybe the result that I wanted to discuss. So X is a Fano variety, and we assume that it has a very nice quantum homology structure. And under this nice structure, I'm going to rule out all the isolated hypersurface singularities that X can develop other than A. That's like, so. And so how is, first of all, I'm going to translate this into symplectic geometry. And the translation is goes as follows. So we, in fact, we need to prove that
Sorry, could you switch the board?
sorry, I'm very sorry again. So let X omega be monotone symplectic manifold. And assume same conditions, so assume semi-simplicity. And then there is no configuration of Lagrangian spheres looking like the D4 diagram. D4 Dinking diagram. And so this looking like means you cannot have a set of collection of Lagrangian submanifolds intersecting at one point transversely in this way. Okay. And why is this enough? So, and how come, like, what is Lagrangian's Lagrangian spheres have to do with this? So, in fact, the reason why symplectic geometers like degenerations or the degenerations is that degenerations produce Lagrangian objects. I won't say submanifolds because it's not always submanifolds, but something that looks like Lagrangian submanifolds. So, in fact, well, let's go back to the degeneration picture. And you have this fiber that you want to study, a special fiber. And let's say we have a singularity here. And if we're in a favorable situation, for example, if we have a high relative ample line bunch on fixed space, you can consider a family of embedding, projective embedding, that restricts to embedding like a restricted XP. Then it will do the projective embedding of XP. And then you can pull back the symplectic form here and get a true form away from the singular locus and define symplectic connection for a given path. Because you can lift the path by using this symplectic connection coming from the form on this the X coming from, and define vanishing cycles. So that is the set inside X that gets crushed into this singularity. So you can look at vanishing cycles. And Seidel studied vanishing cycles for AD, it's a simple ADE singularities. Seidel studied vanishing cycle with these guys, and he basically said that it gives you vanishing cycles are configurations of Lagrangian spheres looking like the dinking ADE diagram. So if you start from an A singularity, then you'll get Lagrangian spheres, M Lagrangian spheres sitting next to each other, intersecting at one point, forming a chain. And if it's a D singularity, then you'll get something like this, E singularity, same, something like this. And I said there's a, isolate, this is the modality zero case of isolated hypersurface singularities. And vanishing cycle, the geometry, the intersecting pattern of vanishing cycles for singularities of modality greater than zero was studied by Elsa Keating. And we have a good understanding of it. It's not like, not draw the picture like this, but we kind of understand it. And what I need to know is that so what is the difference between a singularity and all the rest? So it's that you can find this sphere that's connected to three other spheres. Any sphere has no hands, no neighbors, more than two, maximum two neighbors. This in all the rest, there's a sphere that has three neighbors. Okay. And yeah, Keating proved that by using a property called adjacency. So anyway, going back to this symplectic translation of the theorem, by looking at the vanishing cycles, we're getting a configuration of spheres, and I want to say that there's nothing that has three neighbors. Okay, you only have maximum two neighbors, with my assumption. And why is that? It's actually pretty easy. Yeah. So the two key ingredients. So let's say lemma one. This is what I like to call the okay, so this is what I like to call the quantitative rigidity for Lagrangian spheres. So that I've been talking about sets, but now it's a quantitative rigidity for Lagrangian spheres. So in fact, under the assumption of so semi-simplicity precisely, a Lagrangian sphere L has let's say produces two idempotents, special idempotents that I'll call EL plus minus, for which L is super heavy with respect to these two classes. Okay, and I can tell what I mean by produce is that I can write these idempotents precisely by using the information of L. So but let's suppose we're in even dimensional case, whatever. It's like plus minus 4, well, something, not 8 maybe. L squared, where the squared is taken in the quantum product, and for some number and L. There's a precise description. And why is this possible? There's a result by
Squared means squared in the quantum product?
yeah. So Biran and Members have this result that they call the cubic equation, which says that if you take the cube of the quantum cube of the Lagrange sphere, then you'll get back the class of Lagrangian with some constant in the Novikov field. And so by using this cube equation, you can check that if you square these idempotents, you'll get back the same thing. These are idempotents. Okay. And my claim is that with L is super heavy with respect to these two idempotents that come from the cubic equation of Biran Members. And the second lemma is what I want to call the sharing property. So now, under the same assumption, the semi-simplicity, let's suppose you have two spheres, S1 and S2, forming.
Sorry, I just want to go to lemma 1. You sort of part of it is showing that beta is non-zero.
Yeah,
Okay.
that comes from, that uses semi-simplicity,
Okay.
because if it's semi-simple, there's no nilpotent.
Okay, I understand. Great.
And now let's suppose you have an A2 configuration like this. And as I said in lemma 1, each one of the two spheres produce two idempotents, right? So you have ES1 minus and ES1 plus, and same for S2. You have minus and plus. And the claim is that they have to share an idempotent. They have to share one idempotent, meaning that these two have to coincide. Maybe it's the plus that are the same, but there have to be one, common idempotents if they are intersecting at one point. Okay. So with these two properties for Lagrangian spheres, I can conclude the theorem in the following way. So let's argue by contradiction. So,
Wait, could you just say very quickly sort of a reason why that's
right. So, as I said, description is very precise. And you can cancel the square out and just express this homology class by adding or subtracting. And these two have homological intersection 1, and I use that kind of, so I can calculate, and then there's, I say there's one class that has to make product to a non-zero number.
Okay, so but it essentially follows from this sort of equation.
Right,
And
yes.
the fact that, okay, I see, great.
So now argue by contradiction. So meaning that let's assume there's a configuration that looks like this that I want to exclude. Let's call this S0, S1, S2, and S3. So by lemma 1, each of these 4 spheres produce 2 special idempotents, and the sphere has to be super heavy with respect to those 2. Okay, so let's imagine so it's like every sphere has 2 hands. But now at lemma 2, we're saying that these spheres that intersect have to share an idempotent, meaning that you have to hold hands of each other. So S0, it has 3 neighbors, and it has to hold hands with 3 of them. But from lemma 1, it only has 2 hands. So that means there should be 2 neighbors actually holding the same hand of S0, right? So that means, so these 2, oops. And so that means 2 of the neighbors, S1, S2, S3, have a share an idempotent. But so let me remind you that with respect to those idempotents, these spheres are super heavy, but it cannot be, it's not allowed to be disjoint from the basic property that I said, but these 3 are disjoint, so it's a contradiction. So that's basically the argument. And I think that's a good time to stop. Thanks for your attention.
Questions?
Lemma 1, you briefly said, that L is even dimensional.
Yeah,
Is it
right.
like odd dimensional. So what's this? What, say something about that.
Sure, yeah. So L represents a non-trivial, that's the sphere represents a non-trivial homology class if L is even. Yeah, if the dimension is n is even.
Okay.
But if n is odd, it's not obvious, right? So in that case, you have to kind of use some like a Floer theoretical additional like an analogous argument, but you cannot just do the same thing.
You say
it's actually simpler.
oh, it's simple.
Yeah, it's easier. I forget why, but basically the HF of L, HF of these guys is studied, and it's 1. It's what's spanned by the point, and then you can use that to say that you cannot have. But it kind of reduces to the same spectral rigidity thing. Yeah. But I remember this was the even dimensional case was more involved. Let's say. It was actually.
Have you thought of a way of doing the same, but without spectral invariants?
Yes. Usually, so for the algebraic geometry people, this spectral invariants were actually have been more, it's been used to study dynamical properties, as you can maybe imagine from the origin of spectral Floer homology. But so people who study the connection between algebraic geometry and symplectic geometry usually have a more categorical approach. They study like they build some algebra and do some fancy things. So I thought about, maybe understanding the Hochschild homology of the category generated by these spheres and all that. That's the, I think, usual approach, but I don't know. It should be doable. I mean, it's not that I just lack skills in that direction, so cannot say, but
In algebraic geometry, to what extent this result was it's beyond the dual.
so I spoke to Rahul Pandey,
Yeah.
and he told me that algebraic geometers had lacked tools to say something about higher dimensional cases. 3-dimensional cases are kind of study for, but beyond that they don't have tools. So apparently, not many things. No.
No more questions, then let's thank the speaker.
Thank you.
Thank you.